Now, generating function of Hermite polynomial. Generating function of Hermite polynomial. In case of Bessel function, we proved one thing, that is Jn of x is the coefficient of z raised to n in the expansion of a function. We already see the method. Okay, so the method. So here also we can use the same method or say another generating function. Thereby its coefficient of t raised to n. Coefficient of t raised to n is the Hermite polynomial or Hermite function. Here coefficient of t raised to n. So the function is this one. This one is our function e raised to 2xt minus t square. So we can e raised to 2xt. E raised to 2xt, that form is, expanded form is this one. That is summation over s equal to 0 to infinity 2xt raised to s by s factorial. And e raised to minus t square can be written like this. That is summation over r is equal to 0 to infinity minus 1 raised to r t square raised to r by r factorial. And we are combining these two. Okay. When we are combining these two, here 2x raised to x, here 2x raised to s, and here also t raised to s, here t square raised to r. T square raised to r means t raised to 2r. So t raised to 2r plus s, that is s plus 2r. So t raised to s plus 2r divided by s factorial. Then in order to in order to equate the coefficient, we can substitute instead of s plus 2r. Instead of s plus 2r, we can substitute n. So s plus 2r is equal to n. Then this equation becomes t raised to n. Okay, the same equation and t raised to n. Then now of t raised to n equal to 0 by 2 minus 1 raised to 2x n minus r divided by r factorial n minus 2r factorial. Okay. So what is this? Okay. This formula. Okay. So this e raised to 2xt minus t square is the generator of Hermite polynomial. That hn of equal to minus x. From the generating function, is generating function of e raised to 2x minus t square is equal to t raised to n by n factorial. Minus t. So the equation becomes, that is equation number 2. And when we are combining equation 1 and 2, the LHS is same. So the RHS can be equate. Okay. So the RHS portion equated. We can write that is hn of x is equal to minus 1 raised to n hn minus x. Next, recurrence formula for Hermite polynomial. We can start from the generating function. Recurrence formula for Hermite polynomial. Generating function is e raised to 2xt minus t square, which is equal to summation over n is equal to 0 to infinity hn x t raised to n by n factorial. And we have to differentiate this one with respect to x. So e raised to 2xt minus t square, and with respect to x means we can this one, that is into 2t, which is equal to summation over n is equal to 0 to infinity hn prime x t t raised to n by n factorial. Substitute 1 in 2. That is, instead of this e raised to 2xt minus t square, we can substitute this one in place of e raised to 2xt minus t square. So the equation is 2 into t summation over n is equal to 0 to infinity hnx t raised to n by n factorial is equal to summation over this part. Now equating the coefficient of t raised to n both sides. T raised to n both sides. Then when we are equating we are equating the coefficient of t raised to n. Okay, this one, and multiplying both equation by n factorial. So when we are multiplying here n factorial and here also n factorial, and n factorial can be cancelled, balance hn prime x. Here 2 n minus 1 factorial and n factorial. So we will get a 2n here. That is 2n hn minus 1 x equal to hn prime x. If we have put n is equal to 1, then we will get h prime of x that is equal to 2. Anyway, next equation 1, differentiate with respect to t. Okay, first we differentiated with respect to x. Now we differentiating with respect to t. So the equation is like this, equation number 3. And again substitute 1. Instead of e raised to 2xt minus t square, we can substitute this value here. So this 2x minus 2t. Then instead of this one, we can substitute this form. Then right hand side, RHS, the same thing. Next, equating the coefficients. Now we can equating the coefficients. So 2x h of x by 2h minus x by n minus 1 factorial is equal to h n plus 1 x by n factorial. Next, multiply throughout by n factorial. We can multiply through by n factorial. So here we are multiplying n factorial can be cancelled. Here n minus 1 factorial, here 1 n factorial, then it will become 2n here. Then here 1 n factorial. We are multiplying with the n factorial. So n factorial can be cancelled. Then balance is 2x hn x is equal to 2n hn minus 1 x plus hn plus 1 of x. Substitute 2a in above equation. What is 2a? So this equation. Okay, we can substitute this equation here. Then we will get 2x hn x equal to hn prime of x plus hn plus 1 x. Or we can write hn prime x equal to, this hn prime x equal to 2x hn of x minus this term, hn plus x. Now differentiating with respect to x. Differentiate equation number 4 with respect to x. Then hn double prime x is equal to equation. These two we already know that hn prime x equal to hn x equal to so hn double hn x plus 2x hn prime x minus, instead of h prime and substitute this term. Okay, so this one hn double prime x equal to 2x hn prime x minus 2n hn x. That is equation number 7. Result. Okay, recurrence formula. Now Rodriguez formula or differential formula of Hermite polynomial. So we can start from the derivative function e raised to e raised to x square minus x square is equal to summation over n is equal to 0 to infinity hn x t raised to n by n factorial. Then we can differentiate this function n times with respect to e raised to x square dtn e to the power minus t minus x square. System is dn by dtn is equal to I expanded form like this, that is x plus 1x plus x is to factorial square. Now d by dt of e to t minus is equal minus t minus x square into minus to t minus x. Okay, this term with the t d by dt and d by dt of e raised to t minus x square is equal to limit t tends to 0 minus 1 d by dx of e raised to minus t minus x square. Similarly, limit t tends to 0 d square by dt square e raised to minus t minus x square is equal to minus 1 square t tends to 0 by d square x square. Limit t d and t. So we find out this d and to minus t minus x square. So, okay, now the equation 2 becomes, this equation becomes limit t tends to 0, we can substitute this one, e raised to x square minus 1 raised to n d by dn by dxn e to the power hn n plus 1 plus etc. Okay, now it is limit e x square dn minus square. Then Rodriguez differential equation form polynomial is x equal to minus 1 raised to n e raised to x square dn by dxn e raised to minus square. So, differential form of Hermite polynomial. It's an orthogonality of Hermite polynomial. Orthogonality of Hermite polynomial. The orthogonal property of Hermite polynomial is integral minus infinity to infinity e raised to minus x hn x dx equal to factorial root pi delta. To find out this is the orthogonal property of Hermite polynomial, and we know the delta mn is m is equal to n, it is 1, otherwise it is 0. And we know the hn x is the solution of Hermite equation. We already see in the first session. That is, what is Hermite equation? D square x by dt square dy square minus x y prime plus 2ny is equal to 0. That is h double prime x minus instead of d square by dy square h double prime second differential. Then minus x y prime we can write h prime x plus 2n instead of y x. Which multiply out by e raised to minus x square. So multiply this equation by e raised to minus x square. So e raised to minus x square, e raised to minus x square hn prime x minus x into e raised to minus x square hn prime x plus 2n e raised to minus x square hn of x equal to 0. And I okay, e raised to my okay, next this session, that is this can be write like this, that is where here is no 2, d by dx of e raised to minus x square hn prime x. Here is a 2 here, it is a 2 here, e raised to d by dt of d by dx of e raised to x square hn prime x plus this term, that is 2n equal to equation number 2. Similarly, we can write d by dx of x to minus x square hm prime, here hn prime, here hm prime equal to 2m e raised to minus x square hm x equal to 0, that is equation number 3. Multiply equation number 2, this equation 2 by mx and equation 3 by hnx and subtract. Okay, so we are multiplying equation 2 by hmx and multiplying equation 3 by hnx and subtract. Then we will get hn prime x d by dx of e raised to minus x square into hn prime x equal x minus hmx into d by dx of e raised to minus x square hn prime x, which is equal to 2 into n minus m 2 into n minus m e raised to minus x square hmx hnx. So d by dx of e raised to minus x square is equal to hnx hm prime x minus hm prime x hmx, which is equal to 2 into n minus m e raised to minus x square hmx hnx. And now we are integrating this function with respect to x within the limit minus infinity to plus infinity. If we are integrating this function, this is a derivative of a function. Okay, so integral of derivative of a function is a function itself. So in the RHS we can write the same function here, and in the in the LHS we can write the same function here. In the RHS, integral minus infinity to infinity 2 into n minus x. On applying the limits, when we are applying the limit e raised to infinity minus infinity, that means 1 by e raised to infinity, 1 by e raised to infinity, that is 1 by infinity, that is equal to 0. So this function becomes, which is equal to 0. Okay, so 2 into n minus m integral minus infinity to infinity e raised to minus x square hmx hnx equal to 0, dx equal to 0. For m not equal to n, suppose m not equal to n, then this integral is equal to 0. But anyway, we have to find out the value when m is equal to 0. When m is equal to 0, this function is not equal to 0. So we have to find the value, that is our orthogonality of Hermite polynomial. Okay, so to find integral minus infinity, this function, we have to consider the generating function of the Hermite polynomial, that is e raised to 2xt minus t square summation over n is equal to 0 to infinity hnx t raised to n by n factorial. And we are considering the same another function, that is e raised to 2xh minus h square is equal to summation over m is equal to 0 to infinity hmx h raised to m by m factorial. We are multiplying 5, 6 and e raised to minus x square. 5 into 6 into e raised to minus x square in both sides. So e raised to minus x square, e raised to 2xt minus t square into e raised to xh minus h square is equal to this right hand side. We are multiplying RHS, right hand side of equation 5 and 6. Now we have to integrate this equation with respect to integrating with the from the limit minus infinity to infinity. Then the equation becomes integral minus infinity to infinity, the LHS side and RHS side. Okay, but in this case, this function, this part is 0 actually, because for m is not equal to n, this function, this part will vanishes. Last term will vanish. Uh, we have to find out the value of this one. I can write this function as integral minus infinity to infinity e raised to minus x square e raised to 2xt minus t square e raised to 2xh minus h square into dx equal to integral minus infinity to infinity e raised to minus x minus t minus h square, because here minus x square is here, then minus t square is here, minus h square is here. Okay, so and 2ht, okay, e raised to 2ht into dx. So we can take e raised to 2ht outside of this integral, e raised to 2ht integral minus infinity to infinity e raised to minus x minus t minus h all square into dx. Now we can put x minus t minus h is equal to u. That is dx equal to du. Here dx equal to du. So integral minus infinity to infinity e raised to minus x minus t minus h all square dx equal to, we can write like this, integral minus infinity to infinity e raised to minus u square du, which the value of this integral is root pi. So this term is, so our equation becomes, summation over infinity t h raised to n by n factorial integral minus infinity to infinity e raised to minus x square hnx hmx dx equal to e raised to 2ht into root pi. So in the e raised to 2ht can be expand in this form, expand in this form, and we can write like this, that is summation over n is equal to 0 to infinity 2ht by n factorial. Okay, then the equation becomes, this equation becomes summation over n is equal to 0 to infinity, here t h raised to n, okay, t h here t h raised to n by n factorial square integral minus infinity to infinity e raised to minus x square hnx hmx dx equal to, instead of e raised to 2ht I substitute this one into root pi. Therefore e raised to minus x square hnx hmx dx equal to this, here th raised to n, here th raised to n, and here one n factorial square, here n factorial square, so balance is n factorial here, then 2 is here, 2 is here. Okay, so the equation becomes e raised to integral minus infinity to infinity e raised to minus x square hnx hmx dx equal to root pi 2 raised to n factorial. We can substitute delta mn by combining both them. What both them? When m is equal to 0 and m not m is equal to n and m is not equal to n. M is equal to n, m is not equal to m. Then we can put the Kronecker delta here. Okay, if uh, m is not equal to n, this becomes 0. M is equal to n, then we get this equation.